guys, my name is Vaishnavi. I am studying in Sri Venkateshwara College of Engineering. Subject is District Mathematics. Topic is Lagrange's Theorem. Introduction to Lagrange's Theorem. Lagrange's Theorem is a fundamental concept in group theory. It was named after the Italian mathematician Joseph Louis Lagrange. The theorem provides insight into the structure of finite group. Lagrange's theorem, the most important single theorem in group theory. It helps answers. How large is the symmetry group of a volleyball, a soccer ball? How many groups of order 2p where p is prime? 4, 6, 10, 14, 22, 26, so on. Is 2 to the power of 257 minus 1 primary? Is computer security possible? Etc. Understanding group order. The order of a group G denoted by mod G is the number of elements in the group. Likewise, the order of a subgroup H denoted by mod of H is the number of elements in the subgroup. Lagrange's theorem establishes a relationship between the order of groups and subgroups. Example of Lagrange's theorem. Consider a group G with 12 elements and H is a subgroup of with 4 elements. Then mod of H divides mod of G as 4 divides 12. This demonstrates Lagrange's theorem in action. Exploring subgroups. A subgroup H of a group G is a subset of G that forms a group under the same operation as G. Subgroups are essential in group theory as they help us study the structure or properties of larger groups. Lagrange's theorem provides valuable insight into the relationship between the order of a group and its subgroups. Consequence of Lagrange's theorem. Lagrange's theorem provides a powerful tool for analyzing the structure of finite groups. It allows us to determine the possible orders of subgroups within a given group. This information is crucial in various branches of mathematics and beyond. Application in number theory. Lagrange's theorem has application in number theory, particularly in the study of modular arithmetic. It helps in analyzing the possible orders of elements in finite field and group. The theorem is instrumental in understanding the structure of cyclic groups used in cryptographic algorithms. Statement of Lagrange's theorem. Lagrange's theorem states that the order of a subgroup divides the order of the group. In other words, if G is a group and H is a subgroup of G, then the order of H divides the order of G. This theorem has important implication for the study of group theory. Lagrange's theorem, if G is finite group and H is subgroup of G, then mod of H divides G. The number of distinct left of right coset of H in G is mod of G divides H mod of H. Lagrange's theorem can be formally stated as if G is a finite group and H is a subgroup of G, then the order of H divides the order of G. Mathematically, mod of G equals mod of H. Square brackets G colon H, comma, where G colon H denotes the index of H in G. Proof of Lagrange's theorem. The proof of Lagrange's theorem relies on the concept of left cosets. By participating the group into disjoint left coset of the subgroup, one can demonstrate that each coset has the same number of elements. This leads to the conclusion that the order of the subgroup divides the order of the group. This is the proof. Historical significance. Lagrange's theorem marked a significant advancement in the study of group theory. It laid the foundation for further development in algebra and mathematics. The theorem continues to influence various fields of research and education today. Generalization to Lagrange's theorem. Lagrange's theorem can be extended to the case of infinite groups. In this setting, the group theorem states that the group of a subgroup divides the order of the group if both are finite. This generalization broadens the applicability of the theorem to infinite group theory. Application of Lagrange's theorem. Lagrange's theorem is often used to determine the possible order of groups. It can help classify groups and understand their structure. The theorem also plays a crucial role in study of cyclic groups. Let's consider a group G equals flower bracket 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 close flower bracket under addition modulo 10. If we define a subgroup H equals flower bracket of 0, 5 of G, then mod of G equals 10 and mod of H equals 2. By Lagrange's theorem, G colon H must be 10 by 2 equals 5, indicating that there are 5 left cosets of H in G. Limitation of Lagrange's theorem. While Lagrange's theorem is powerful, it always provides a divisibility relationship between group and subgroup orders. It does not grant the extents of subgroup of a specific order within a group. Exploring the structure of groups further may require additional theorems and techniques. While Lagrange's theorem is a valuable result in group theory, it does not provide information about the existence of subgroup of a specific order. The theorem only grants divisibility relationship between the order of groups and subgroups. Additional techniques and theorems may be needed to explore more complex group structures. Lagrange's theorem. Theorem. If G is a finite group and if H is a subgroup of G, then mod of H divides mod of G. For what class of groups did we already know this to be true? Note that if G and H are as in the theorem, then mod of G divides mod of H is just the number of cosets of H in G. More generally, since the following definition can apply to infinite groups also. The index of H in G denoted of G colon H is the number of cosets of H in G. Example, what is the index of phi z in Z? And what is the index of 2v is to in D4? Lagrange's theorem and cyclic groups. In the context of cyclic group, Lagrange's theorem provides a powerful tool for analysis. It allows us to determine the possible orders of subgroups within a cyclic group. This information is essential for understanding the properties of cyclic groups. Illustrating Lagrange's theorem with an example. In a group G equals flower bracket E, A, B, C, D, F with operation. Composition. Let H equals flower bracket E, be a subgroup of G. The order of G is 6 and the order of H is 2. Applying Lagrange's theorem, we find that G colon H equals 6 divides 2 equals 3, implying that there are 3 left cosets of H in G. Implication of Lagrange's theorem. Lagrange's theorem provides a powerful tool for analyzing the structure of groups and subgroups. It helps us determine the possible order of subgroups within a given group. Understanding Lagrange's theorem is crucial for exploring the properties and relationship within a group theorem. Lagrange's theorem in cryptography. Lagrange's theorem has practical application in the field of cryptography. It is used in algorithms that rely on the properties of groups to secure data. Understanding the implication of Lagrange's theorem can enhance cryptographic protocols. Application in cryptography. Lagrange's theorem finds application in cryptography, particularly in public key encryption schemes. Understanding the divisibility relationship between group and subgroup order is essential to secure cryptographic protocols. Cryptographers relate this theorem to ensure the security and efficiency of encryption algorithms. Extension of Lagrange's theorem. There are extension and generalization of Lagrange's theorem or advanced group theory. This extension offers deeper insight into the relationship between groups and subgroups. They provide a more comprehensive understanding of group structures. Generalization and extension. Lagrange's theorem has been generalized and extended in various directions by mathematicians. Expansion includes Slovane's theorem, which provide more detailed information about the structure of finite groups. This generalization have further enriched the study of group theorem and its application in diverse mathematical areas. Connection and permutation groups. Lagrange's theorem also applies to permutation groups, which are groups that consist of permutation of a finite set. The theorem helps in determining the possible order of subgroups within permutation groups. Understanding the structure of permutation groups is essential in combinatorics and group theorem. Importance of Lagrange's theorem in mathematics. Lagrange's theorem is a foundational result in group theory with wide-ranging application. It is a key concept in algebraic structures and has implications in various mathematical disciplines. Understanding Lagrange's theorem is essential for exploring the properties of groups. Practical application of Lagrange's theorem. Lagrange's theorem has application in cryptography, coding theory, and algebraic geometry. It is used in various algorithms and protocols to ensure the security and efficiency of computational process. Understanding Lagrange's theorem is essential for professionals working in fields that rely on group theory concepts. Conclusion. Lagrange's theorem is a fundamental result in group theory that provides insight into group structure. It states that the order of a subgroup divides the order of the group with important application in mathematics and cryptography. By studying Lagrange's theorem, mathematicians can deepen their understanding of groups and their properties. Thank you.